Hi, welcome to this recording for Unit 53. Unit 53 talks about basically the solar activity. This is basically the activity that happen on its surface, because that's the thing that we see, and that's the thing that's going to impact us the most. So what we're going to talk about in here is that how is this solar activity related to Earth? We're going to talk about the sunspots and what causes them and their properties, and we're going to talk about describe the solar cycle and how it's related to the sun's magnetic field, and also discuss the solar activity and its effects on the climate here on Earth. Okay? So basically, one of the things that were discovered early on by Galileo when he looked at the sun with a telescope, he saw that it has dark spots. And so these sunspots were something of a puzzle initially, until the science of spectroscopy was developed further and noted that when you run a spectrometer to the region of the sunspots, you will see that the spectral lines of any element, it doesn't matter which, are split into different lines. So in the regions where there is no magnetic field, there is no splitting. In the region where there is a magnetic field, there is a splitting. So that we understand that, I mean, this is related to magnetism, and let me explain why that is. First of all, spectrometer is similar to when you have the phenomenon of rainbow, basically white light from the sun immediately before the rain or after rain, because the air is saturated with air molecules. The light that comes in from the sun is going to enter the droplet of water, and then is reflected from the inner surface and comes out refracted from the other surface, is split into different colors. If you take a prism, for example, and you run the light through it, the white light through it, it's going to also split it into different components. So that's basically what the science of spectroscopy, except in this case, the light that is coming from that region has elements in it, okay? Molecules around it. So the light that is coming from the sun, some of it is absorbed by those elements. And if those elements, under normal circumstances, they're going to exhibit definite spectral lines. For example, the famous hydrogen line, which is 656.5 nanometers, that's the red light from hydrogen. But if you have a magnetic field now, strong magnetic field in that region of space, that line splits in two, and you will have, separated by small finite separation, a few nanometers. That is basically the Zeeman effect. So we know that it has to do with magnetism. So these sunspots also are related to magnetism. That means that those are regions of strong magnetic field. So that's how we know what we know about the sunspots. Okay. Well, there is another phenomenon also we know, at least from the experiments here in the laboratory, and that is if you have a strong magnetic field, these are the field lines of the magnetism. You have a North Pole on one side and a South Pole on the other side. The North Pole, there are field lines that you can find by the iron filings, are moving from one side to the other. If you drop in a charged particle moving at a certain speed, then that charged particle will spin downward to the South Pole, or swim or spiral upward to the North Pole, depending on its charge, if it's positively charged or negatively charged. Okay? Depending also on its velocity. So that means that these sunspots are regions where this different ions, positively charged ions and negatively charged electrons, they're pinned on the surface of the sun, which causes those regions, because they're pinned, they have less motion, they're frozen, if you wish, relatively speaking, of course, compared to the rest of the surface of the sun. That means the temperature in those regions is lower than the temperature of the rest of the sun. That's why they appear dark. Okay? These regions, the sunspots, are super big. They're much bigger than the Earth. Okay? They can swallow the Earth several times over. So here is how the phenomenon works. Pinned ions on one side and electrons on the other side, depending on which way they were moving, actually, too. So, but they are pinned on the other side by the magnetic field, this super strong magnetic field. will prevent the sun from releasing heat under those layers as much as it does, because this is the convection layer immediately under the surface of the sun. So that's how the sun gets rid of its excess heat, through convection process. So it's like boiling basically. And here there is no problem. The surface temperature is the average surface temperature of the sun. Except in here, when this layer tries to rise to the level in here and get rid of that heat, it finds particles that are not easily able to move, as opposed to the rest of the surface. Hence, this area of the sun is of a lower temperature compared to the rest of the sun, at least on its surface, at least on its photosphere. Okay, so that's basically what causes sunspots. So there is kind of an arc in here that forms between the north and the south pole, in this case, of the magnetic field. And these are the field lines. So there is a trap, basically, a huge amount of matter, ionized matter, that is trapped in this region. Of course, it's in a motion one way or the other, it doesn't matter. But it's actually trapped in this region of space that forms these huge arcs, okay? This is how they look like from distance. These are prominences that form around the surface of the sun. Okay, this is how they look like. Okay, at times, these prominences, they entangle from one another. When they do, in this case, that amount of matter from the sun is ejected in a coronal mass ejection, CME. This can be very, very powerful and devastating to anything that it encounters. The good news is the sun is big, and most of the times the CMEs, they are ejected in directions other than the Earth. But when they do come to the Earth, they can wreak havoc over our electrical systems, our satellites, our grid, like what happened in the 1988 or 89 in the Northeast, and also in the 1800s. So these things can cause a lot of problems that could have severe consequences, at least in our transformers and electrical grid and other electronics. And we'll talk about how they break, okay? Because it has to do with the fact that we have this prominences and the fact that the sun actually is spinning, and it's not spinning at the same rate throughout the sun. So basically, some portions of the sun are moving a lot faster than others, namely the equator is moving a lot faster, which causes it to cause these lines to start to twist. And when they do, they can at times entangle, they entangle with one another, and they are released in space. They snap, basically, into space. In addition to that, you have solar flares. Solar flares, they're most of the times not as powerful as the CMEs, but they also can cause all kinds of problems. And both the CMEs and also the solar flares, they constitute what is known as space weather. This is one branch of basically science where they monitor the activities on the sun, and they issue warnings. Different kinds of activities can be, or at least the intensity can issue. There will be warnings basically issued depending on the intensity and the direction of this ejections from the sun. Here is an example of a CME. It's a very, very huge area that it's going to go through. And let's say, for example, the Earth is on this side, so most of these things is going to miss the Earth. But if the Earth is really on the cross path of these things, albeit the Earth is far away by the time it reaches it, so it's going to be really diluted, but it still can have a lot of. This can extend to the far edges of the solar system. Okay. On Earth, this activity can cause basically at least the auroras, the northern and southern lights. And I explained that early on. Basically, is that when this charged particle hit the upper atmosphere, the first thing that they encounter actually is the magnetic field of the Earth. So it serves as a kind of a first level of protection, because of the fact that There is a magnetic field from the Earth that points from the south actually to the north, because the south is actually the northern magnetic field. Uh, so some of these charged particles, they are going to be directed toward the North Pole, others they are going to be directed to the South Pole. They come with tremendous speed. So what happened in this case, which are mainly protons and electrons, so that you know. Okay, so that's the particles that are in this CMEs or coming from the sun. So when they hit the upper layers of the atmosphere, they interact with the oxygen, and in this case, they basically the oxygen, which causes them to eject or to basically emit light with different colors. You see them in the green in this case, and that's depending on the transition of the oxygen molecules in this case. Depending on the activities, this northern light or southern light, they can extend over huge areas. That they can come very low in the from the north, okay, to not to the equator, but at least to some latitudes near the northern hemisphere and also the southern hemisphere. Okay. Well, the solar cycle, it turns out that there is times when the solar activity peaks and then dips and then peaks again. The cycle takes about 11 years. Okay. And if you do the math correctly, it has to do with the rotation of the sun and the fact how often it is, so that before those entanglements are coming. So in other words, the sunspots, they increase and they decrease on a cycle that is 11 years. So between this peak and this peak is 11 years, and somewhere midway, which was five and a half years between the two peaks, there will be a solar minimum. Okay, so that's phenomenon that is noted all the way throughout, and it's recorded from the 1800s all the way to now. Okay, so this is basically what I was talking about in here early on, and that is because the sun is mainly a gas, so it's not a solid surface like the Earth in here. So the speeds in the equator is faster than the speed near the North Pole. As a matter of fact, if you could stand the North Pole, you should really have no speed at all. Okay, and and you can see it in here. It's only 25 days to go once around the sun in the equator, whereas it takes far longer near the poles, and it's going to even slow further down as you get to the North Pole. The point being in here, imagine with me that there are some field lines in here, so they're going to be pushed further on the equator than they do on the different latitudes of the sun, okay, whether north or south, and that what forms this magnetic field regions. And at some point, again, like I said, this pole starts to form, and when they do, at times, because of the difference in rotation speeds, they cause them to snap. Okay, and that's really what causes the CMEs. Okay. If we look at throughout the history of the sun, we will notice that at least from the recorded times into today, there was a time when this activity was super minimum. Okay, that almost drove the Earth to, at least it was a little ice age. I mean, the temperature went down from the 1650s to almost century. Okay, with basically the entire sun kept quiet with not much of a lot of basically CMEs forming and things like that. That caused a mini or a little ice age. The reason for this, called Maunder minimum, is unknown. Okay, this is something that scientists are trying to understand. This record in here, or this graph in here, is kind of has some good news and some bad news in it. Okay, the good news is we are supposed to be in where the sunspots on average they are down actually, which causes, if we look at the data from before the 1980s, down, which is supposed to cause less effect, if you wish, on the heating of the surface temperature of the seas. Before that, there was a one-to-one correspondence. There was a correlation. As the number of sunspots increased with it, the surface temperature of the seas also increased, caused the warming, if you wish, on the Earth. Well, the bad news is the Earth continued to warm, at least the sea surface of the world temperature continued to warm, albeit that this sunspot numbers went down. So technically, if it was not for a human activity, this sea temperature should have gone down and did not. Because we have added human activity, so we are causing, or at least something else is causing, the increase in temperature of the sea surface, as opposed to the sun by itself, which could have caused it to go down. So if these sunspots were even higher than this, probably would be even in a much more terrible state than what we are right now. So again, this is the unit about the solar activity and its effect on the Earth. And the roots of the whole thing is actually has to do with the magnetic fields of the sun and how it spins around its own axis. Thank you.